This is the Daily Space for today, Thursday, July 30th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today, we can yet again congratulate yet another space agency for launching yet another mission off on its way to Mars. Today, NASA successfully launched its Perseverance rover along with the Ingenuity helicopter on their 7-month mission to arrive at Mars on February 18th, 2021. So far, everything is looking great, and we look forward to things continuing smoothly until we are faced with the terror of landing. But for now, it's still 2020. And it's impossible to know what new terrible thing is going to make murder hornets and squirrels with bubonic plague look normal. Showing us that things could indeed be worse is a new paper in the Proceedings of the Royal Society A by Constantine W. Anscheit and Daniel H. Rothman. These two MIT researchers have shown that we are just one massive volcanic ash cloud away from global glaciation. To those of you with Yellowstone, Katla, and Naples all erupting on your 2020 bingo card, you really don't want that to happen. Now, to be fair, any one supervolcano or massive eruption probably can do us in, but not do in the climate too badly. But widespread eruptions or some kind of biologically induced cloud formation could reflect enough sunlight back to space to, well, bring a terrible, terrible ice age to the planet Earth. It turns out that a sudden drop in the amount of sunlight hitting the surface of Earth can cause the ice caps to expand, which sets up a feedback so that as the ice expands, it reflects more light back to space, further dropping the amount of energy that warms our world and thus allows the ice to expand even further until, well, eventually the entire planet is one cloud, or rather one large surface of ice. Now, as the ice expands, it kills off vegetation, coats over forests, and our Snowball Earth, with ice sheets that even coat up the algae, we'll have a buildup of carbon dioxide, and that buildup in the atmosphere allows a greenhouse effect to eventually warm the Earth up enough that snow retreats and forests and grasslands can return. This has already happened multiple times in Earth's past, and according to this new research, this phenomenon may be common to otherwise habitable worlds orbiting other stars. For those of you keeping score, this means that life can die both by fire and by ice, even on a planet in a star's habitable zone. We see how runaway greenhouse effects can ruin environments like that of Venus. This is a permanent death to planets that worlds just can't return from. We now understand how the global ice ages in our own history may have occurred, and we see in our own existence and in the fossil record that life can and does rebound from ice ages. It just may be different life than was around before the ice age. This teaches us two really important things. First off, finding a world in a star's habitable zone does not make that world habitable. It could either be a greenhouse-baked death trap like Venus, or snowball like our Earth has periodically been in the past. Second, while Robert Frost thought death by fire was something he might desire, I'd like to state there is no coming back from that less traveled path. Ice is nice. Pick the ice. We've said it before. and we're going to say it over and over again in the future. The universe is trying to kill us. Destruction exists at every size scale we can observe, and it is out of the carnage we see that we have to try and create an understanding of our universe's past. One of the more commonly destroyed structures in our galaxy are families of stars. From shredded dwarf galaxies to shredded globular clusters, every new star survey has found new streams of stars that were formed when tidal effects from a galaxy, our galaxy, stretched a system out into a thread of stars of similar compositions and motions. A new paper in Nature with lead authors Yan Wang describes a newly discovered star stream. Found by the Southern Stellar Stream Spectroscopic Survey, or S5, this stream was identified through the careful study of stellar motions. Careful follow-up found that these stars also shared the same extremely low heavy element content. As a reminder, in astronomy, we have hydrogen, helium, and we count everything else as a heavy element. And in this case, those stars are mostly hydrogen and helium, indicating that the material in the stream had been enriched by a minimal number of supernovae before these stars formed. The stream is located in the direction of the Phoenix constellation. And when I say these stars have minimal heavy elements, I mean we have never seen a globular cluster this metal poor before. It's impossible to know if the stars in this stream originally came from a globular cluster or a dwarf spheroidal galaxy. These two kinds of systems can contain similar numbers of stars, and in rare cases, dwarf galaxies can have a single epoch of star formation, just like we see in globular clusters. In the paper, the team argues it is likely that the progenitor of this stream was a globular cluster. They argue this because it's more often that globular clusters have a single burst of star formation and consistent metallicities than for a dwarf galaxy to have a single burst of star formation. And the thing is, though, it can happen. There are dwarf galaxies out there with single epochs of star formation. Now, the thing about saying that this is a globular cluster is that would mean we need to rethink the history of globular clusters, which we thought could only form after the universe had undergone a certain amount of enrichment. And we thought forming globular clusters required more heavy elements than are seen here. Now, they also argue that in order for this to more likely be a globular cluster, well, more globular clusters are seen orbiting our galaxy in the direction of these stars than dwarf galaxies are seen orbiting in the direction of these stars. But there are dwarf galaxies with single epochs of star formation. There are dwarf galaxies orbiting in this direction. And given the choice between this being a super rare object that was destroyed or a more common object that had to break the rules as we know them to form, I would have gone with this as a destroyed dwarf galaxy. Either way, whatever this was, this is a stream of stars with a less complex chemical makeup than we've ever seen before. And that's kind of awesome. This is a blob of stars that formed together out of something very pure that hadn't been enriched by that many supernovae. And we've never seen this. And it's kind of awesome. There are lots of times in science when more than one theory could explain what we are observing. And there aren't always tests to determine which of the two theories matches reality. Take gravity. We know Newtonian equations work at human scale velocities and masses. We know relativity works at extremely high masses and velocities. What we don't know is if space-time is loopy or stringy at the smallest of scales. While string theory so far hasn't won anyone over with its testability, It has captured people's imaginations thanks to popular books by Stephen Hawking and Brian Greene, among others. The theory that has been trying to make predictions, however, is loop quantum cosmology. In a new paper in Physical Review Letters, a team led by Abhay Ashtekar is able to explain both the large-scale power spectrum's anomaly in the cosmic microwave background at low values, and also the anomaly in lensing amplitude that shows inconsistency between, well, the observed cosmic microwave background and lambda cold dark matter cosmologies. They refer to this solution with loop quantum gravity as a cosmic tango that elegantly captures reality at the largest and smallest scales as it works to bring together quantum physics with, well, the largest structures in our universe. According to Ashtekar, the standard inflationary paradigm based on general relativity treats space-time as a smooth continuum. Consider a shirt that appears like a two-dimensional surface, but on closer inspection, you can start to see that it is woven by densely packed one-dimensional threads. In this way, the fabric of space-time is really woven by quantum threads. In accounting for these threads, loop quantum cosmology allows us to go beyond the continuum described by general relativity, where Einstein's physics breaks down. For example, beyond the Big Bang. This paper is the first to consistently explain both these known anomalies. Co-author Dong-Hyai Jeon adds, the recent study in the journal Nature Astronomy proposed an explanation for one of these anomalies that raised so many additional concerns. They flagged a possible crisis in cosmology. Using quantum loop cosmology, however, we have resolved two of these anomalies naturally, avoiding that potential crisis. In addition to solving these two known anomalies, this paper also makes new predictions about a fundamental cosmological parameter and primordial gravitational waves that might be testable by future planned space missions. These aren't some pie in the sky, someday if we develop new technology, maybe we can. These missions currently under development can say if we are right or wrong. This is not yet definitive proof that loop quantum gravity is real or a nail in the coffin of string theory, but it is definitely a paper that made me sit up and take note. I now have a small hope that we'll have a unifying theory that brings gravity into a quantum context, and sometimes a small hope is enough. And that rounds out our news for today. This has been your Daily Space.